received her PhD from Kirkwood, and had postdoctoral positions in Ohio State and in Arizona. Alice works on many different things, both in theoretical and observational astrophysics. She works on galactic dynamics, dynamics of planetesimals, and today her talk is about the bulge in the Milky Way Galaxy and a model for it.
Yeah.
Thank you.
So here's the less pretentious title. So resonant heating model for the shapes of bulges. So I put all the important pictures from the talk up. So this is from, these are views of a barred galaxy in a simulation. And you can see, so this is the top view, and this is side-on view, so the bar is this way. So this is the vertical structure, and that's a head-on view, so it's viewed that way. And you can see that as the disk, in time, as you move through the simulation, you pick up this thing that people call the peanut shape, and sometimes people call it an X shape. So you can see both in the literature. And in this particular simulation, there's an asymmetric stage. So people call that bar buckling. And so that there's actually a real galaxy that shows the same type of feature. This one is pretty dusty. In intermediate inclination was one of the few that shows the peanut shape that's not an edge-on galaxy. So when you're looking at a galaxy, you don't usually have the ability to flip it and view it from different viewpoints, right? So if edge-on galaxies, you can see this structure, and in face-on or moderately inclined, you can see bars. So this one is one of the few that's you can see both the bar and the peanut shape. And I actually discovered this one, so it's kind of cool. And so that's my data. So how do you explain this? So one way is to think about global instability, and so people talk about buckling instabilities. Another way is to think about the orbits, and so this shows you one type of orbit that might be important in this buckling, not in this peanut shape. And then this shows you level curves of a Hamiltonian model, which I made to try and predict the orbit shapes, and then to try to actually pin down what are the stars that are supporting this bizarre shape, and how do they get in that shape, in their, what lifted them off the plane. So I'll talk about the Hamiltonian model also. So why are we looking at this? Well, and why did I go back to this? So I worked in that image. So in some sense, this is over a long career. So this image, in the days when I was an infrared astronomer, so that's like 1997. And then I worked on a Hamiltonian model in 2002. And then I revived it last year. So why did I do that? And the reason is that there are big surveys going on of the Milky Way where properties of not quite a billion yet, but there will be properties of a billion stars are being measured. And so it's really an opportunity to dissect the Milky Way and really understand what's going on in it. So we can think of this as a big challenge. How do we learn stuff if we have observations of a billion stars? And so I like to think of it not just as can we figure out what the shape is and what are the orbits that are supporting structures that we see, but what constraints on the evolution of the galaxy can we make when we measure things in the Milky Way? So the reason I revived my Hamiltonian model for vertical structure is because a new structure was discovered in the Milky Way from current ongoing surveys. So before I talk about that, I want to talk a little bit about role of resonances and the interpretation of this peanut-shaped bulge in our galaxy. One thing that you need to pin down the mechanism is that if it's related to the bar, so you need to know about the bar pattern speed. So I'm going to explain a little backstory involving the bar pattern speed. So I don't know how many people have seen this plot, but this is the velocity distribution in the solar neighborhood. So it's nearby stars to the sun. They had to be near enough and bright enough that intelligence were seen and measured with the Hipparchus satellite. So this is the solar neighborhood distribution that, made from the Hipparchus samples. And it shows various clumps in it that are interpreted. They've got names associated with which clusters are in them. And this one out at the bottom is called the Mercury stream. So important is the radial velocity. So it's a velocity distribution. So what you do is you count all the stars and you make this plot based on the number with radial as a function of radial velocity. And the tangential velocity where 0 is the circular velocity. So this stream, this clump down here, there's kind of a gap here, and there's a clump down here. It's separated by 50 kilometers a second from 0, and 0 is what a circular orbit going through the solar neighborhood would have. So how do we, this plane, this velocity field, I can call it this, I call it the UV plane, where U is the radial and V the tangential velocity component. So how do you interpret that in terms of orbit structures? Well, you can take the energy of an orbit and divide it up into circular motion and epicyclic motion. So, if you have an orbit with epicyclic oscillations, it looks like this. It's like a rosette. But when you're on the UV plane, stars, you know the radius. And so the V of the velocity sets the angular momentum. So because you know the radius, so R times V gives you the angular momentum. So really what you see is you see is if you're far away from 0, you can measure the epicyclic amplitude on the UV plane based on how far away it is from that 0 point. So interpreting the UV plane, circular orbits are in the center, and these ellipses tell you the epicyclic amplitude. And R times V is the angular momentum, so V sets the angular momentum, which sets the mean radius of the orbit. And so these are these green curves. And if you want to, you can measure the epicyclic amplitude by the location on this plot. So another way to think about that is, so since the V is setting the angular momentum, or the mean radius of the orbit, the things with positive V's are orbits with high angular momentum. And so that means they have to spend most of their time in the outer galaxy. They just happen to come into the solar neighborhood. So they're at the bottom of their epicycles. Whereas the stars down here are stars that are spending most of their time inside the solar neighborhood, inside the solar galactocentric radius. And they just happen to be coming out to the solar neighborhood where we're seeing them in the solar neighborhood. So keep that in mind. The V is setting the mean radius, and it's setting the angular momentum of the orbit. So we can ask, well, what's the analogy in the celestial mechanics regime? So in the celestial mechanics regime, if I take the asteroid belt and I plot the positions of all the asteroids, I don't see any patterns. You just see this even distribution. So this is, in fact, is positions of asteroids at some particular date that I got off the Minor Planet Center. And you don't see any structure. But if you plot in terms of semi-major axis, then you start seeing the Kirkwood gaps. Well, so in hindsight, that's kind of obvious, right? Because the semi-major axis sets the period of the orbit. And so if there's a resonance with something, you're only going to see it if you plot an orbital period. So in the galactic setting, what sets the period? Well, the thing that sets the period is the angular momentum. So if we go down in V, we're actually changing an orbital period. So if you just think of this plot and going down in V, at some point you will hit a resonance with something if there is a big perturbation in the system. So the galaxy has got this bar in it. As you go down in V, you hit this resonance with the bar, and there's a gap in the distribution. And that explains this dip that separates the stars here from separates the stars there. So it's an outer Lindblad resonance, which tells you that outer Lindblad resonance means that there's two epicyclic oscillations per single rotation in the bar frame. So what does that actually mean in a different way? So why is this resonance giving you a gap? Well, when you're actually on resonance, there are big perturbations. You don't actually have no orbits when you're on resonance. What really happens is you have no circular orbits when you're on resonance. So there's show that co-rotation tends to be outside the length of the bar. It's not that the length of the bar is exactly known. Then you think, well, we're even further outside. What's the only resonance, strong resonance? It's got to be the 2 to 1. And
we don't have any other constraint on the pattern speed.
No, actually, until the peanut, which I'll get to.
Okay.
So, yes.
So none of those surveys can map any stars in the bar.
Which surveys?
Gaia or something like that?
Yes, Gaia should map stars in the bar. So I'll get to the next step of survey, and then we'll go even deeper in a second. But yeah, so you're kind of jumping ahead, but the point I'm about to make is that because resonances are narrow, and we scale with the perturbation strength, usually something like this, some power of it, you get a tight constraint from their location, and that led to very tight measurement on the bar pattern speed. So I went and looked up the 2 most recent constraints on the bar pattern speed, and it's percent. It's quite good. And they're a little bit different. So Gardner and Flynn, they were using a backwards integration technique, whereas Ivan, who's a student working with me, was doing forward integration and also using a more constant constraint. But these are they even agree, but this is a pretty small error bar. So we can really think of the bar pattern speed as very nicely measured. That's actually really good compared to almost any other measurement in the galaxy. Actually, so it's nice.
What do you mean, or constant constraint?
So he was looking at the C, Oort C, which is measures like a streaming ellipticity type measurement. So he was using the Oort C measurement.
I am not well educated. What again is Oort C?
Oh, okay. So the Oort constant. Yeah. Well, so that's one that when you have a slight instead of having pure sine and cosine, you have a slight shift. So it's like you have. So the mean rotation isn't a circle. It could be slightly non-circular motion for the bulks of the stars.
Good. Okay.
Yeah. Yes. There's also a K. You can take Oort constants. If you assume everything is circular, then you only get A and B.
Right. Okay, that's what education and
Okay. So the location of the resonance should be different in different neighborhoods. Okay. So if we know where it is in the solar neighborhood, if we went inside the solar neighborhood, we should be closer to the resonance. And if we go outside the solar neighborhood, we should be farther from the resonance. So if I make these UV plane plots in different places in the galaxy, I should see a shift of this gap, actually. So so Hipparchus didn't go very far, but the RAVE survey went a little bit farther than Hipparchus. And so this is a very recent result from the RAVE survey, where Teresa and her collaborators actually looked for this shift of the Hercules stream for different neighborhoods that are just inside and outside of the solar neighborhood. And you can kind of see if you put this green thing on, that the solar neighborhood, it's at one distance, and the solar neighborhood is slightly farther away than the other ones. So, it changes depending upon whether you're inside or outside the solar neighborhood. So that's crude data, but it's kind of the thing you can look for, consistent with what you expect, if the gap separating the Hercules stream from the rest of the stars is really due to the outer Lindblad resonance with the bar. Okay, so now let's move on to surveys towards the Milky Way Bulge. So I'm going to talk about the photometric surveys. So they're just looking at lots of stars, and then they're making color magnitude diagrams. And they deep involve the luminosity distributions at different positions on the sky. So to do that, you need to know what the luminosity distribution should look like if you had one population. And so I took this from a paper that just came out a couple weeks ago, where they show the luminosity distribution. And so you have asymptotic giants and red giants, and then you have this big thing called the red clump. And so whatever luminosity distribution, you're seeing stars at different distances, then you deconvolve with this function to try and get the numbers of stars as a function of distance at different positions in the bulge. So using this survey called the VVV survey, which is like 2 mass, so it's a near-infrared survey, but it's a lot deeper. So you have a lot more stars to do this with. And this is an example of distributions that they get after they've deconvolved with this function. And so this is galactic latitude, longitude, and then around 0, which is, and it's been shifted to 0, so that's the galactic center. And then in this direction, they actually just wrote distance. So this is covering the galactic center, which is supposed to be right in the middle here. And then you can see these 2 clumps showing up at different distances. So what we're looking down the galaxy, and then at some particular height. So these are all at different heights. So these are different. Each panel's at different heights. So at some particular heights, you're seeing 2 clumps of stars. So it's like you're seeing stuff in front and stuff in behind. And then on the other side, you're seeing the same thing. So at a different height, you're seeing 2 clumps. And so that's what gives people, they draw this X, and they say we're seeing an X shape. So that's kind of a complicated picture, but that view of do I see 2 clumps, the 2 discovery papers for this X in the Milky Way, that's how they did it. So if you go and look at their papers, you'll see them talk about the distributions at different distances from the galactic center. So this is Veg and Gerhardt's model for the galaxy based on those previous maps. And this is the face-on view, shows the bar. But that bar is actually longer, so this is an oval-shaped bulge now. So the bar actually extends more than a couple kiloparsecs. But this is the side-on view, and this is showing you this peanut shape in side-on view. So these are beautiful. I mean, it just came out a couple weeks ago. So, I wrote a paper on this summer, but if I'd had these data, I would have had much tighter constraints on the model. So how is this made possible? Well, these big surveys like the VVV and the Model 3, so some of the discovery, I think the TOPS work was based on the Model 3. So those surveys led to this discovery, so you need to make it clear who discovered this, that David Nataf and Williams and Zuccali, they wrote papers very almost back to back. They came out almost exactly the same time. But they're building on the work of Chris Stanek, who really pioneered this using the red clump to figure out distance of stars. And so he has an early paper using the ogle data to see the galactic bar. So, this is as important because that's the technique. So we know that, so in our galaxy, we're sitting in it, so we see an edge-on view. So peanut-shaped galaxies are not uncommon. Edge-on galaxies often are peanut-shaped. And so this shows you one of them. This is an optical viewpoint. This is a redder image, so you can see it dustling in the middle. And the isophotes show you this peanut shape. And then if you do an unsharp max scheme, you pull out this X. So here's another place why people call it an X shape. And this is from one of Martin Bureau's papers. So I mentioned before, in rare inclined cases, you can actually see both. So this is the spiral galaxy, and this is an optical band. And we discovered this one in the near-infrared survey. So you couldn't actually tell from the optical data that it was peanut-shaped. We only saw this square-shaped bulge thing appear in the near-infrared data because of all the dust in this galaxy. So Martin Bureau, in 1998, as part of his thesis, he did a survey of peanut-shaped galaxies and showed that the velocities in those galaxies were different than non-peanut-shaped galaxies, and that they were typical of bar galaxies seen face-on. So he really established that these peanut shapes are really a barred galaxy phenomena. You do not see peanut shapes in non-barred galaxies. So you can ask the opposite question. So do all bars have peanut shapes? And I think depends who you talk to, but Victor de Batista thinks he has examples of barred galaxies that don't show peanuts. So it may be that not all barred galaxies have peanuts. I think they all should, actually, but I disagree with you. Okay, so the explanations for why you get this vertical structure. So most of the simulations of bar galaxies actually showed that bars would buckle. And this shows you a simulation, one of the GALMER simulations, where you see the same buckling. So the problem with the bar buckling instability is that it doesn't predict where you're going to get the peanut. It's like, it's an instability that's sort of based on this a dispersion relation, so it's not very predictive. That's the problem with it.
So I don't understand centrifugal. Those vectors are up and down, right? In the z direction.
Well, so if this thing is, then did I flip the arrows as possible? So self-gravity should flatten it out, and this thing, I have a force that way, because it's like,
But I don't understand how centripetal force could be the vertical direction.
huh? Could what?
I don't understand how a centripetal force could be the vertical direction. I understand
It's
your
just
one
the,
vision.
it's just the, so you have to think of this as so I tried to try the front and the back, so it's like it's a U-shaped thing, so it's bending. So think of these two together like this, and as the orbit is going like that, the acceleration, it keeps having to change its direction, so it's an acceleration down. The self-gravity can keep it together, keep it from happening. So just think of an orbit like this, and this is being pulled. Okay, never mind. We can talk about
Presumably
this.
it's a lower energy state then. Is there a way to understand that?
This thing, you can do the perturbation theory, perturbation expansion exactly the way like a bar instability is. It's just you take into account, you get a dispersion relation. You just have the sign flipped, and then Landau damping shuts it off.
So generally, if
Yeah.
dispersion, if the velocity distribution was too anisotropic, they want to become less anisotropic, basically. Because very, very roughly speaking, this is sort of what's happening. You get more of a vertical component of the
I'm not sure how that makes things less isotropic, but you know,
anisotropic.
I don't like this model. So
Oh,
okay, I mean we could talk about it more, but it's not predictive, and it's also.
I still don't understand what it is, but anyway.
Oh, okay, yeah.
Is this related to the bending instability?
It is the bending
It's the
instability.
same thing.
It's the same thing. It's the bending instability. Do you have a way to explain the?
No.
Yeah, okay. I can show it. If you take a hose and you like put air through it, then the hose bends. And it's the same thing. It's because any small perturbation can grow in it. So,
So this X-shaped features would be a transient feature that leads to a post-up.
right. That's the standard scenario, which
But
I
you're
was going to
saying
say isn't the whole story. Yeah.
they're long-term.
Right.
fit.
I'm going to say that's not the whole story. Yes.
But what you showed us is that those features are present in the older stars, the redder stars,
Yes.
but not in the young stars.
So with
they
that,
sort of,
yeah, it's a whole bulge. But the reason it's the whole bulge is because there's a Let me explain what this is wrong, and I'll show you why it's wrong in a second. Okay. So you're making me jump ahead. I don't want to jump ahead. Okay. Because I'm telling the whole story here. So the other viewpoint. So there's the fire hose or the bending instability viewpoint, which most of the simulators use to explain peanut shapes. Then there's earlier work by Daniel Fenneger and François Combs where they actually took n-body simulations and they measured the potential, and then they ran orbits in it. They looked at the shapes of orbits, and so this actually shows you a little bit more modern view of that. So these are they looked for periodic orbits in potentials measured from real 3D simulation, n-body simulations. And you can see these U-shaped orbits. So here's an upwards U and a downwards U. And those are you can call them banana-shaped orbits because they look like bananas. And then there's also this other class, these figure 8 things. And then you can actually make things like bifurcation diagrams that show so that up these U ones, they call them bananas and banana plus and banana minus. So you can see where they appear on these as a function of Jacobi integral and where their maximum Z is. So, this body of work suggested that there was a vertical resonance responsible for making the peanut shapes, and that it was comprised of orbits like these banana-shaped orbits. So of bar buckling. And then, so I can't remember which one buckles and which one doesn't. One of these doesn't buckle. That one buckles, yes. Did you see the buckle? But now it's after it's buckled, and the peanut shape is still growing. Okay, so, and here's another one. So this is the one that I keep showing people because they're like, oh, all peanut shapes are because of bar buckling. And you show, this simulation doesn't shows a peanut after a while, but there's no bar buckling. So yeah, so you can see it now. It's got a perfectly healthy peanut shape there, and it never buckled.
How many orbits?
So these are running for a couple gig a years. So I don't know how many orbits that is. It's quite a few.
What are the initial conditions?
Oh, right. So these are not my simulations. These are GALMER simulations. And so they're, the GALMER made this database of n-body simulations to look at mergers, but they have a couple comparison isolated galaxy simulations, so we just took those. And I was just looking for any simulations that showed peanut shapes. So I just asked Ivan to find me a couple, and he knew the GALMER database really well, so he just gave me these.
But they're not equilibrium models. I mean, they're like.
Okay, so they're not based on Milky Way models, no. And they have live dark matter. So if depending upon how the dark matters, so there is a debate. Like one thing, these simulations show the bars slowing down, and if you run simulations without live halos, the bars may not slow down. So the reason these peanuts keep growing, this one after their bar buckling, the reason the peanut keeps growing is because the bar's slowing down. And this one has a perfectly fine peanut shape, but each bar is also slowing down. So if our Milky Way if the bar didn't slow down, it might be different. So I've been dissecting these to figure out what's going on in these, but I know that they're not necessarily the true galaxy, right? Okay, so I went into those simulations to try and figure out what was actually, giving you the peanut shape. So I'm going to dissect them to figure out where resonances are and all that stuff. But the first thing I did was look at the velocity distributions. And so if you plot this, in this one I have angular momentum. So I'm plotting for different neighborhoods along the bar. I'm plotting the z component of velocity versus angular momentum. So I may have there are various ways to plot the velocity distribution. So it's not quite a velocity, it's angular momentum versus the z component. This is the z angular momentum, so it's only set by the angular momentum, the z component of the angular momentum. So it's only velocities in the plane. So, but what you see, so these are this is the outer disk. So the outer disk is cold, and it's vertical dispersion and slow, so it's skinny here. And but then if you go into inside some radius, all of a sudden inside some particular angular momentum value, the whole disk is puffed up vertically. So all of a sudden you lose all the in-plane orbits at some critical angular momentum value. So this is why it's probably resonance, right? Because angular momentum is setting the resonance. We saw that with the bar earlier. So here it's the same thing. Inside here we have thick disk, and outside we have thin disk. And this, I pulled out velocity distributions for stars above and below some height, and so you can see the same type thing in the higher stars too. And then each panel is at different times. So so I think I moved the green line because the bars are slowing down. So at later times, as the bar slows down, this critical angular momentum that's setting whether the disk is thin or thick is moving outwards. So what do we actually see in the simulation? So bars slow down, some bars buckle, others don't. The peanut shape keeps growing even after the bar buckling phase. So this is while the galaxy is symmetric. And within a particular angular momentum value, the stars are heated. And we don't see cold populations, cold meaning in the plane populations within this value. But we also don't see cold populations at all. So, if I was going to think about a resonant interpretation, to decide whether I want a resonant heating or a resonant trapping model. And if I trap in resonance, I can take a small population of stars in a small region in phase space and lift them, and then they would still be a small region in phase space. But I did not see that, meaning I only see hot and cold. So that's why I'm heading towards the resonant heating scenario rather than the resonant trapping scenario. So I think the resonance is more important than the history of bar buckling. Although, you know, when you think about a vertical resonance is going to depend on the vertical oscillation frequency. The vertical oscillation frequency depends on how thick the galaxy is. So as galaxy thickens, the vertical oscillation frequency drops. So previous bar buckling can change the thickness of the disk even if it's not setting this peanut-shaped feature. Okay, so vertical resonance. So this, instead of a commensurability between the epicyclic frequency and the rotation, it's a commensurability between the vertical oscillation frequency and the angular. So this is the angular rotation rate. You subtract the bar angular rotation rate. It's as if you're in the frame moving with the bar. And so this is telling you that you have 2 vertical oscillations per orbit in the bar rotating frame. So if I take this relation for the frequencies and I integrate it, then I get an angle. So this is integral of the vertical oscillation frequency is it's an angle that depends on where you are in the oscillation. This is the angle, azimuthal angle on the sky, and this is the bar angle. So as the bar moves, and if this is true, then this angle is approximately constant. So we can call that angle a resonant angle. And when I make a Hamiltonian model, it will depend on that angle. So the periodic orbits, those are orbits that go up and down twice per rotation period. The banana plus and minus banana orbits, these are orbits that have fixed thetas, or phi's here. So a particular, so phi 0 gives you one class, and phi equals pi gives the other one. And the other thing that you can do with this frequency, so if I just rewrite this as a new minus the difference in rotation, angular rotation rates, I get a frequency that is a way to quantify how far away from resonance I am. So that this delta parameter is 0 when you're exactly on the resonance, and it's less than 0 when you're inside and positive when you're outside of resonance. So, this kind of tells you why you get these particular shapes of orbits for periodic orbits. So those are the banana orbits. So how do I make a Hamiltonian model? So first let's ignore the perturbation from the bar. So if I ignore the perturbation from the bar, then I can write the Hamiltonian for a particle in orbit in the galaxy, and instead of using Cartesian momenta, I can use action angle variables. And I can expand to low order in all the actions. So this JR is the action variable that's related to the epicyclic motion. And JZ is the action variable associated with the vertical motion. And so to low order, this is just first order with something that doesn't depend on either. This thing just sets the angular rotation rate in the galaxy. And then these coefficients in front here, this is the epicyclic frequency, and that's the vertical oscillation frequency. So I can take any, axi-symmetric system and figure out how to write this. It comes down to doing an expansion in low orders of JR and JZ and figuring out what functions here. So I don't have to assume I can put functions of angular momentum in front of every coefficient rather than expanding as polynomial of angular momentum. And then you get these extra terms, that second order terms. So to think about that in a different way, so how do I go from the action angle variables back into the Cartesian variables? So Z is just a cosine of the vertical, the angle associated with the vertical oscillations, and then this JZ sets the height of the oscillations. And if I were going to think about the drawing just the Hamiltonian that depended on just JZ, I would have a Hamiltonian that looked like that, and the level curves for the Hamiltonian would be circles Okay, so remember z is related to the, in action angle variables like this. So supposing I have the bar perturbation. The bar perturbation has I can decompose it as a sum of Fourier components. And so here's a Fourier component in the bar that's moving with the bar. And if it's symmetrical around the midplane, it will depend on z squared, not z. And so I'll pick the z squared version of it. And then I take z squared and I just put this back in and do some expansions. And so z has a cosine phi, z squared has a cosine squared phi. And then I can write that out as a cosine 2 phi z. And then I take the sum of the cosines and write it out as a sum and a difference. And then you can recognize here that this is my resonant angle. So what this does is it tells you how to take any Fourier component and write it in terms of action angle variables. But so this will be the perturbation term that's associated with the m equals 4 Fourier component of the bar. So if I take the unperturbed Hamiltonian and I add in the bar perturbation, so I have a second order term, and this is my distance to resonance. And I've done a canonical transformation, so actually this angle is now an angle for the Hamiltonian. I get a Hamiltonian that looks like this for each term. So the term here depends on the bar strength. This is the distance to resonance, and this comes from the vertical structure of the galaxy. So the level curve, so if I draw level curves of that Hamiltonian have this particular structure. So this is, for those of you guys who are used to celestial mechanics, this is a second order resonance, a mean motion resonance. It looks exactly the same. And second order because it goes to z squared, which is like inclination squared instead of inclination for this system. So what I plotted here is level curves in this coordinate system. So in this coordinate system, theta is phi, is the angle, is the angle on the plot, and the radius from the origin is this jz, which tells you the vertical height of the orbit. So if I lift a star, then I'll put it in a high jz orbit. It'll have a high value of jz. So if you look at a large negative delta, then the level curves look like this. So things that are right here 0 are orbits in the plane. And if I go to a large positive delta, I get orbits that are in the plane. These are down here. But in between here and here, or here, between here and there are no orbits in the plane. So the level curves just show you that nothing stays in the plane in this region. So there's a particular range of angular momentum values in the galaxy where there's no orbits in the plane. So if I put a star in there, it's going to get lifted out of the plane. So and I can actually one more thing. I guess I can phi equals 0 gives me the banana ups, and phi equals pi gives me the banana down orbits. So I was reading about bifurcation diagrams and decided it'd be kind of fun to draw a bifurcation diagram for this. So this shows you the periodic orbits, which are fixed points in this Hamiltonian, one-dimensional Hamiltonian system. And so as you go down in delta, all of a sudden the stable orbit here bifurcates, and you get two stable orbits, and the one in the middle at the separatrix is unstable. So it shows you two stable orbits being born, and unstable orbit being born. And then out here, you get, again, two more stable orbits are born, and only two more unstable orbits are born, and then the ones in the middle are stable again. And this part here, you can actually take that model and predict the level, the bifurcation of the banana minus that's seen from the numerical integrations. So there's a clean way to turn this into that. It's not quite linear, but it goes this where you have to turn the j into a z height, and keep track of the fact that this is energy and that's not energy. But you can actually take this and turn that into that. So in 2002, when I was making the Hamiltonian model, I knew that within the resonance there were no orbits in the plane. So what I proposed that you structure. But that, what? Yes, Chris?
I don't understand how the level curve in the left map onto what you just said.
Oh, okay. So what I'm showing you here is this is a function of distance from resonance.
Right.
But as you grow the peanut shape, you can also think of it's like you're stretching out these plots also. So a star that's here, and then you grow the bar will get lifted up into these regions, and then after it's grown.
What's the horizontal coordinate here?
Okay, so x is I can go back to the coordinate system. So the angle on the plot is the resonant angle, and the radius on the plot is it's like the inclination of the orbit. So after the bars, where am I?
So far you only discussed the regular orbits, right? But these features will tend to be erased by chaotic diffusion.
Yeah, I suppose you could have.
So what's the role of chaos?
I don't know. So far, I haven't explained anything with chaos yet. So, and actually, the resonant trapping model doesn't work. This is a model that I proposed in 2002 when I couldn't measure anything. So, so the reason it doesn't work is that the resonances are really narrow. And so you go from, so I thought that I would get this kind of X shape from going in and out of the different sides of the resonance. The resonance is really, really narrow in real galaxies. But in 2002, I didn't even know which resonance was the important one. I couldn't even figure that out. And so I wrote it up for any possible vertical resonance. So now I actually know which one it is. so that's the reason to look at the simulations. I didn't know which resonance, and I didn't know how strong it was. So I measured those from the simulations. Okay, so the other thing that can happen is the bar can slow down or the disk can thicken. And then if you go in these level curves, if you start off with some thing, you either slow down the bar or thicken it by keeping it the same strength. Then you go from one to the other. But the thing to notice is if you start off on this side, you start off in a circular orbit, or non-circular, this orbit in the plane, and then the planar orbits disappear. And so the resonance actually moves outwards, and things that are outside the resonance get pulled into the resonance. But they don't wind up in these islands. They wind up in the separatrix of the resonance. So the heating is really different. So this picture where the bar slows down gives you a really different picture than if it speeds up. If it speeds up, you wind up lifted into these islands, and then you have a population of stars that are really confined in phase space. But if you're heating, they wind up pushed into the separatrix, and you wind up with a very large dispersion, which is what I think you see in the galaxy. So I showed you that you got this Z. Well, when I picked the potential perturbation, I picked the m equals 4 Fourier component. So why did I pick the m equals 4 component? So the way to think about this is if you have a star that it goes up and down and up, because if the galaxy is symmetrical, it feels a plus push here and here and here, and then when I map that down in the plane, I get pluses in the potential on 4 places, and that's an m equals 4 structure. And so the m equals 4 perturbation in the bar excites the vertical resonance as long as the galaxy is axi-symmetric. So you could worry about that and say, well, the m equals 4 is not that strong, but so is it strong enough? And that's another reason to look in the simulation, measure how strong the m equals 4 Fourier component in the bar potential is, and that'll tell you if the resonance is strong enough to actually account for the peanut. So that's what I did, and so this shows you actually the m equals 2 and the m equals 4 components as a function of radius, and this is done for each vertical position. And so you actually have to know how they depend on z squared, the coefficient that depends on z squared for these things. So I spent a lot of time trying to actually measure this from the simulations to see how strong they were. So this is how I tested the model. So first I took the simulations and I took the axis-symmetric potential. I get the rotation figure out where the resonances are in the simulation. And then I take the Fourier components as a function of z squared, and I measure their strength. And that tells me the width of the resonance. And all of these things are functions of well, not the width, but everything is a function of radius, so that I can plot everything. So the first thing is, are the peanut shapes in the right place to be associated with this vertical resonance? And the answer is yes. So if you plot omega minus nu over 2, and you plot it, you look to see where it crosses the bar pattern speed, and that tells you where the resonance should be, and that's about in the right place. And for these simulations, the bar is moving outwards. This cross moves out. And it's convenient to look for the Lindblad resonance with the cyclic frequency. The Lindblad resonance was inside. And that's actually nice because then you can separate out the radial degree of freedom from the vertical degree of freedom. So if the two resonances were on top of each other, it would be a lot harder to do that. So if you go back to the Hamiltonian model, this only tells you how far away from resonance you are. So the resonance itself, the strength, and also the libration time scale are only set by these two parameters. And this epsilon is a frequency. And so you can figure out where is the resonance actually important. And it turns out the resonance is really only important when this is smaller than that. And there's this divided by that actually tells you how high the orbits are in the resonance. So the separatrix orbit has this height. And you can also estimate the libration time scale, which also tells you how fast it takes. If I put an orbit in the separatrix, how long does it take to get excited? So if it takes a Hubble time, your model's no good, right? So I need to check that the excitation time scale is short enough for the resonance to actually lift the stars out of the plane. So this shows you the distance to resonance and the widths of the resonances. So when I said the resonances are narrow, these bars show you the widths, this condition that this epsilon strength is that you're close enough to the resonance for it to be important. And so they're very narrow, so you can't explain. So I can't explain the extent of this structure with a broad resonance. It has to be something that's all done within a very narrow range in angular momentum space. And so this is one simulation. This is the other simulation done at different times. The other thing that's useful is the heights on this plot are the strengths of the resonances, and that's a frequency that's the same as the libration frequency. So it tells me the time scale for things to happen in the resonance. So the other thing I can do is predict the heights of the orbits in resonance. And when this worked, this was great. So it looks, maybe not doesn't look all that exciting, but in each of these plots, I take the point where I cross resonance and then predict the height of the orbits there. And the great thing is that I get heights of about a kiloparsec, which means that the resonance is strong enough to explain the heights of the stars in the peanut shapes. So even though they're narrow and the Fourier component is not that big, this A coefficient, this thing, is pretty small. And so this Z for the height of the orbits turns out to be pretty large, actually. So the new model, so since the resonant heating model, the resonant capture model doesn't work. The new model is you start off with stars that are in the plane just outside resonance. And as the resonance moves outwards, those stars are now kicked up into the separatrix. And then as the resonance keeps moving outwards, those stars move out here and they become more and more just like stars evenly distributed in the galaxy. So you can ask what stars are capable of actually supporting an elongated peanut shape that's actually in phase with the bar. It's actually only aligned with the bar. And those have to be aligned angles either along 0 or pi. So as you get further and further out, they stop supporting the bar eventually. So only the stars really near the separatrix of the resonance are going to support phi angle goes in a circle. So they tend to look like that. So they're kind of peanut shaped, but a little bit lopsided. And then if I actually looked at, so that would be orbits from one of these circles. If I had an orbit that was further out like this, then it would spend some time looking like a banana up and sometime looking like a banana down. So it would look like this orbit with another one flipped on top of it. And so it would have kind of a shape like that. So it really would look like a peanut shape. So the last thing I want to say is, so is this a precision measurement, right? And so I have a very narrow resonance, just like the outer Lindblad resonance. What can I say about our galaxy? Because I'm interpreting a detected feature in terms of a narrow resonance. So, well, it turns out it's pretty hard to calculate the vertical oscillation frequency. And so it's better if you figure out some other way to do that. And so what I did is I take Poisson's equation, and this stuff is just related to the rotation curve, because it's all derivatives with respect to r. And d phi squared dz squared is actually the vertical oscillation frequency in the midplane. And so you take Poisson's equation in the midplane and relate the density in the midplane to the vertical oscillation frequency and things that depend on the rotation curve. And then if you have a resonance, you can replace that with other stuff that depends on the rotation curve, but now also depends on the bar pattern. And so what I get is a function of density that depends on radius that should be actually equal to the density in the midplane only on resonance. So it turns out to be a constraint on the midplane density at the location of resonance. So now I have a prediction. I know the midplane density is some spot in the Milky Way. Can I get a Milky Way model that will tell me what that density is? So the answer was really hard. So I contacted a bunch of people, but Sanjeev Sharma is working on the Galaxia model. He actually took the Galaxia routines and gave me density as a function of radius in the midplane, and also gave me rotation curve information so that I could plot the density of calculated in this way, and to look to see where do they cross.
What is Galaxy?
Galaxia. It's a so the observers really want to know how many stars and whether the rotation makes sense, and so they make these big these prescriptions to predict photometric numbers of stars that they would detect in any direction, for example.
Form a given model.
Right. So there's a big industry in making galactic models for this, and they have underneath there's some mass distributions, but can you get them to give you a rotation curve out? It's really hard. So yeah, so I succeeded. I succeeded in asking them, and that one person replied and actually helped me come up with a rotation curve. In some sense, it's important because if you have all these people trying to model the galaxy and you can't figure out if there's a resonance anywhere because nobody will tell you what the mass distribution is, it's really frustrating. So this plot shows you all my attempts to do this. So I went and generated the, so with a rotation curve and the known measured bar pattern speed, you get this curve, this rho LR curve. And then you can plot that versus other estimates for the midplane density. And so the two important lines here are the Besançon model rotation curve predicted rho and the Besançon density for the same thing. And those two curves cross right there, which is actually about where people say the VNet is. So these other curves are different ways of trying to get the same thing, but the Besançon model tells you that the PNet is at 1.3 kiloparsecs in our galaxy, and that's pretty much what people are seeing. And you can kind of envision this error bar shrinking at some point. So it looks like a big error bar, but right now it's telling you that everything's consistent. If we use it more, we'll get a really tight constraint on a mass model in the center of the galaxy.
How does the density become negative?
How does the density become negative? It just tells you rotation curve isn't well known. So whatever you fit to it, you get, you're taking derivatives of the rotation curve, and those derivatives aren't accurate. Density can't become negative, yes.
So which of these curves should we believe?
Okay, so some of them, like Malhotra's rotation curve, they didn't actually have any points in the center of the galaxy, so it's totally extrapolated. The Sofui's rotation curve, he's compiled lots and lots of data, so that one's not too bad. So those are the green. And the error in the Sofui's one actually plotted what if we had a 2% error in the bar pattern, and that's those two lines.
But what's the difference in the assumptions of the input to Sofui's and Besançon?
Okay, so the Besançon is some huge compilation based on photometric stuff and a little bit of rotation. So Fui's rotation curve is actually compiling lots of CO and H1 data.
But it was gas.
Yes, that's right. But they didn't take out non-circular motion and other things. So, right. So that's why I think this error bar should be. One could shrink it. It's pretty big. This circle is big, but it's something that one could probably improve by an order of magnitude.
But are we to believe that there's been some convergence here?
What?
I mean, the black and green curves represent the improvement of all the other curves, which are all over the place in the inner galaxy.
So have I improved on the density yet? No.
No, I mean just these existing models that you're showing.
Okay, so in order to improve upon it, first thing I need to do is take the X shape.
No, I'm asking about it, but before you got into this.
Yeah.
These rotation curves, I mean, these density profiles, I mean, do we believe that green and black represent some converged result?
So how many people have taken the rotation curve and tried to decide what it actually is in the center galaxy? I think I didn't see anybody doing that, actually.
Oh, well, okay.
So.
But when you say you're plotting that,
I don't know what your question is. So is the question, is this an improvement or not? This is right now I feel like it's a self-consistency check because I'm predicting that the resonance is at the right location. And it's consistent, at least very consistent with the Besançon model.
Why should we trust the Besançon model more than the other model?
look,
Yes.
what I see here is the mass density as a function of radius.
Yes.
It's in a spherical model, at least, you can easily get that from a rotation curve. So I thought that what you're plotting is basically the implied density profile for those rotation curves.
Oh, okay. So
you're
what
working
goes
fast.
into these models? So the so first of all, so the center of the galaxy is not round, so it's an axi-symmetric thing. You've got a thick and thin disk. You've got multiple populations of thin disks. You've got dark matter, which is actually important, even though you're way in the center. You've got a bulge. All of these, the bulge is also, so there's like 6 different components of things to get the midplane density, which all of those could have errors in them, and nobody knows, and most of them aren't measured at 1 kiloparsec.
Maybe we should keep going with this.
Okay.
3 minutes.
Well, I'm almost done anyway. So what are the metallicities of the stars in the X? So there's a certain amount of observational studies measuring metallicities of those same stars in the big photometric surveys. And so I'm predicting that the stars that are seen in those 2 populations on either side of the galaxy should be disk stars. They should be exactly like the stars just outside of the resonance. So the stars are fairly metal, well, they're not metal poor. So I think the observations are telling you, yes, that this is maybe consistent with what they're seeing. So meaning they're not really young or old. They're not really old. So they could be disk stars that are just outside, like disk stars that are just outside of the resonance. So yeah, so I'm actually at the summary. So the penis shape, I think, is caused by this outward motion of this resonance. It doesn't matter about the bar buckling, although the location of the resonance does depend on what's heated up the disk. So the Hamiltonian model actually lets you predict where the resonance is and how high the orbits are, and tells you the shapes of the orbits in the resonance. And it's a heating model. So I think as the resonance moves out, the stars are lifted. And that it also tells you that the stars in those X's are all in the same energy and momentum region. So they have very similar values. Then so far the midplane density, the bar pattern, and the rotation curve are all self-consistent. at the location of the resonance. So, but haven't gone further to actually make another measurement, meaning an improved measurement hasn't come out, but we certainly have a consistent measurement for all those three things. So there's lots of things that aren't done. And so I haven't gone past just checking self-consistency to figure out what constraints I could put on the inner galaxy. And this model's based on looking at simulations where the bar slowed down. But it would be nice to know if the galactic bar did slow down. So we don't actually know that yet. So how far has the resonance gone? Can we actually tell? So as the resonance keeps going, the stars start losing their coherence with the bar. But they're still hot. So they're hot in the sense that they still have they're still vertically excited. So one could look for a change in the vertical heights in the inner part of the galaxy to see if you could figure out how far the resonance has gone. So I couldn't figure out a way to tell if the bar buckled. So one thing I looked for is there evidence in the distributions from the previous episodes of bar buckling. So one of the reasons I couldn't do that is because it doesn't wind up being in phase with the bar again. But maybe there's a different way to do that. And the data that just came out a couple weeks ago lets me now makes it possible to actually measure the m=4 component in our galaxy, which I couldn't do before. And so one could actually really, instead of just saying it worked in simulations, find out, is the bar strength in our galaxy the right strength to explain those orbits. So, and I completely neglected the radial degree of freedom. You actually need the radial degree of freedom to pin down the angular momentum of the resonance itself. So the orbits in the center of the galaxy are not round. And so if I'm saying the peanut's at some particular distance along the bar, that's not the same thing as saying the peanut is at some particular angular momentum value or radius value. So pinning down the actual location of the resonance involves knowing the ellipticity of the orbits in that region, which I think we can now predict using the latest observations. So, but I couldn't have said that 3 weeks ago. So I'll finish there.